Enlarged lymph nodes are often symptomatic of metastatic tumors and inflammatory diseases. Radiologists routinely examine lymph nodes for staging cancer and assessing treatment response. As a manual task, this can be very tedious, time-consuming, as well as vulnerable to human error. In this work, we develop an improved system for automated detection of enlarged lymph nodes. A previous approach of ours, presented at MICCAI 2014, worked by decomposing 3D volumes of interest of lymph node candidates into a series of 2D views, thereby circumventing high-dimensional 3D feature computation. Histograms of oriented gradients features, known as HOG, were computed directly on the raw CT intensity images. An SVM was then trained to classify candidate views based on these features. Here, our core hypothesis is that by leveraging mid-level semantic boundary queues of lymph nodes, we can develop enhanced input for HOG computation. These enhanced input maps will be learned from manual annotations produced by radiologists on a training set of CT scans. To build our datasets, we collected CT scans covering 2 target regions of interest from the National Institutes of Health Clinical Center. A radiologist then manually segmented any enlarged lymph nodes encountered. After decomposition of each lymph node candidate into 2D views along the axial, coronal, and sagittal planes, we have a corresponding set of binary images delineating the manually labeled lymph node boundaries. Computing our semantic feature maps, which will serve later as mid-level input for HOG, begins with training a lymph node-specific contour detection system. Lymph nodes exhibit substantial variation in shape, implying a wide spectrum of boundary contour appearances. Seeking to capture this distribution, we first extract all binary patches from the training set with a center pixel residing on a lymph node boundary. K-means clustering is then performed on these lymph node boundary patches to define distinct contour classes, known as sketch tokens. Here, we see a subset of the resulting cluster means. Large variation in contour appearance is evident for lymph nodes, as well as for colon polyps, which we display here for comparison. With K-defined classes, we can train a random forest for multi-class classification on input CT patches. The center pixel of an input CT patch can be assigned K+1 probabilities, corresponding to the K contour classes and the background class. The first boundary Q map we derive is constructed by taking the pixel-level sums of the K probability values output by the sketch token's random forest. This map may be interpreted as the total probability of each pixel residing on a true lymph node boundary. Because any true boundary pixel should fit optimally into at least one of the K contour classes, we also compute a map consisting of the maximum pixel-level sketch token probability values. Histograms of oriented gradients can now be computed on each derived boundary Q map, in addition to the original raw CT intensity image. The result is a 3-channel feature map. Contained within this enhanced map is higher-level, semantic information derived from the pre-processed lymph node selective visual responses. We then use these features to train an SVM for binary classification of 2D views as either containing a lymph node or not. The SVM scores for views sampled from the same volume of interest are averaged to obtain the final candidate-level predictions. We train and test our models for each target region separately. Evaluation is carried out via 6-fold cross-validation across disjoint sets of patient CT scans. The 3 input maps, sum map, max map, and the raw CT intensity image, allow for 7 distinct integrations of feature sets to be tested. All 6 integrations that include at least one boundary Q map end up outperforming HOG on raw intensity alone. The top-performing feature sets exhibit 24 to 39% greater recall than the baseline HOG at clinically relevant low false positive rates. Additionally, the system achieves higher recall in the mediastinum than the recent deep learning approach to lymph node detection, which was presented at MICCAI 2014. Unlike a CNN trained for direct lymph node recognition, our pipeline includes an explicit semantic boundary layer. In conclusion, we propose a novel method for automated lymph node detection which leverages hybrid image feature maps based on object boundary queues. These learned maps can be used in place of or in addition to raw CT intensity images for HOG feature computation. Evaluation of our approach in 2 target regions demonstrates that the mid-level information supplied by the new representations leads to an enhanced feature set for this complex object recognition task.